This presentation will give you an overview of the impacts of climate change on urban forests with a special emphasis on the Midwest and Northeast. Let's start by defining urban forests. For the purposes of this course, I mean all publicly and privately owned trees within an urban area, including individual trees along streets and in backyards, as well as stands of remnant forests. You may be sitting here thinking, why should I care about climate change and what does that mean for urban forests? We know that urban forests can provide a wide variety of benefits to help cities mitigate climate change, such as taking up carbon dioxide and reducing heating and energy use through creating windbreaks and shade. They can also help us adapt to current and future climate change by helping to improve air quality, reducing the urban heat island effect, and helping to control stormwater. Cities recognize the important role urban forests play in climate change mitigation and adaptation. When coming up with climate change action plans, more than a third include trees as part of their solution. At the state level, almost 2/3 of climate action plans include trees, and 84% of cities view trees as part of their overall climate change protection efforts. But urban forests also face challenges from a changing climate, such as changes in drought during summer months, flooding, increases in severe storms, and changes in pests and disease that impact urban trees. Before we talk about the specific impacts on urban forests, let's first review the changes we're already seeing in our climate in the Midwest and Northeast and what we can expect to see over the coming decades. The colors on the map show temperature changes over the past 22 years from 1991 to 2012 compared to the 1901 to 1960 average. As you can see, changes have been more dramatic in the Midwest and Northeast, which have gotten about 1.5 degrees Fahrenheit warmer over that period, while areas in the southern Midwest and Southeast have not changed much or even gotten cooler in some areas. The frost-free season length, defined as the period between the last occurrence of 32 degrees Fahrenheit in the spring and the first occurrence of 32 degrees Fahrenheit in the fall, has increased in each U.S. region during the period from 1991 to 2012, relative to the 1901 to 1960 average. Increases in frost-free season length correspond to similar increases in growing season length. The Midwest has a 9-day longer frost-free season on average, while the Northeast has gotten 10 days longer. Changes in precipitation are even more variable. Many areas in the Northeast and Midwest have gotten much wetter, increasing by 15% or more. But there are areas that have gotten drier, most notably in northern Wisconsin and the upper peninsula of Michigan. Not all of this precipitation has been falling evenly. Over the historic record, heavy precipitation events have increased 40% on average across the United States. Trends towards more intense precipitation are particularly clear in the Midwestern and Northeastern United States, with the Northeast experiencing the biggest increase at 71%. Sea level has been rising globally over the past century by about 8 inches, but local impacts vary due to post-glacial subsidence and rebound along the East Coast. Observed sea level rise in Philadelphia has significantly exceeded the global average, increasing the risk of impacts to critical urban infrastructure in low-lying areas. From 1901 to 2012, sea level increased 1.2 feet over this area. Looking forward, what can we expect over the next century? Scientists use climate models to project changes in climate under a range of possible greenhouse gas emission scenarios. These models are then scaled down to the local level so we can understand what changes may be in a particular city. These maps show modeled changes in mean annual temperature for the end of this century compared to the end of the last century under two greenhouse gas emission scenarios. The one on the left represents a scenario where dramatic reductions are made in emissions, while the one on the right represents a business as usual scenario. Even under the low emission scenario, we may have warming of 2 to 6 degrees Fahrenheit, which is many times the rate we experienced over the last century. And under the high emission scenario, warming may be 8 degrees or higher. These maps show change in surface air temperature at the end of this century relative to the turn of the last century on the coldest and hottest days under a low and high emission scenario. Note that we expect to see more dramatic increases in winter low temperatures than in summer high temperatures, but both are expected to increase. These maps show projected changes in the frost-free season at the end of the century. Under a low emission scenario, the frost-free season could be up to 20 to 40 days longer, and under a high emission scenario, the frost-free season could be 40 to 60 days longer. The effect of warming will be even more pronounced in cities due to the urban heat island effect. This figure shows surface temperatures in New York City on a summer's day, with temperatures in populous urban areas being approximately 10 degrees Fahrenheit higher than the forested parts of Central Park. Dark blue reflects the cold waters in the Hudson and East Rivers, and the light blue reflects the cooler temperature in Central Park. In addition to changes in temperature, we also expect to see changes in precipitation. These maps show seasonal precipitation change for the end of this century compared to the end of the last century under low and high emission scenarios. Large increases are projected in the winter and spring in the Northeast and Midwest. In the western Midwest, precipitation could remain constant or decline in summer. Hatched areas indicate that the projected changes are significant and consistent among models. White areas indicate that the changes are not projected to be larger than what could be expected from natural variability. Like we've observed recently, it's expected that heavy precipitation events will increase in the future. These maps show simulated changes in the average amount of precipitation falling on the wettest day of the year for the period 2070 to 2099 as compared to the 1971 to 2000 average under a low and high emission scenario, suggesting that heavy rain events will deliver even more precipitation in the future. Although precipitation may increase, we could have some increases in dry periods as well. These maps show simulated changes in the annual maximum number of consecutive dry days, or days receiving less than 0.04 inches or 1 millimeter of precipitation. Stippling indicates areas where changes are consistent among at least 80% of the models used in the analysis. This suggests that areas in Ohio, Kentucky, southern Indiana, and Illinois may experience an increase in consecutive dry days. With warming temperatures, sea level is also expected to rise. Under a low emission scenario, sea level is expected to rise by about 0.5 meters, that's about 1.5 feet, under a high emission scenario. And sea level could rise up to 2.5 meters or 6.5 feet by the end of the century under a higher emission scenario. Couple this with the storm surge and local geology, and many coastal areas are at considerable risk. Now that we have a general understanding of how climate has been changing and is expected to change in the future, what are some implications for urban forests? One obvious effect is that warmer temperatures can lead to changes in habitat suitability for trees. My colleague at the U.S. Forest Service, Louis Iverson, and his team have developed models to look at these projected changes in habitat suitability using a statistical model based on U.S. Forest Service forest inventory data. These projections are available for 134 species on a free online climate change atlas. I'll walk you through a few examples of projected changes for a few common tree species in the East. The first one is sugar maple. This is one of our most iconic species for the Midwest and Northeast. The map on the left here shows its current range, with areas in dark green and blue representing the most suitable habitat, and the red line representing its current range limits. Under a low emission scenario, habitat for sugar maple is projected to decline in the southwestern edge of its range by the end of this century. This loss of habitat is expected to be even more severe under a high emission scenario, extending into eastern Ohio and Pennsylvania. The most suitable habitat for Honeylocust is currently Missouri, Illinois, and Indiana. Under both a low and high emission scenario, suitable habitat is projected to shift north into Iowa and southern Wisconsin for this species. Sweetgum is a species more associated with the southeast, but habitat suitability could stretch into parts of Massachusetts by the end of the century under a low emission scenario and up into Maine under a high emission scenario. The maps I showed you show how habitat may change for individual species, but how do we expect habitat will shift for forest communities? Using the same tree atlas models, Dr. Iverson's team has also modeled shifts in habitat suitability for specific forest types. These maps show projected changes in forest composition by the end of the century. They project a loss of spruce fir habitat that is currently common in northern Minnesota, northern Wisconsin, and the upper peninsula of Michigan. They also show an expansion of suitable habitat for elm, ash, cottonwood up into many parts of the northern Midwest. Maple beech birch is expected to lose habitat in places like northern Indiana and Ohio. And habitat suitability for oak hickory, shown in green, is projected to expand into many parts of the Midwest. These maps show changes in habitat suitability in the Northeast. Note the different color scheme. Here, spruce fir habitat, shown in green, is expected to be completely lost, even under a low emission scenario. Oak hickory habitat is expected to expand across much of the Northeast, at the expense of maple beech birch. The Climate Change Tree Atlas is a really valuable resource for native species and forest types, especially in their natural habitats. But we know urban areas are filled with other types of trees. Non-native species used in cultivated settings, many cultivars, and of course invasive species. For species where we don't have more sophisticated habitat suitability models, we can look at changes in plant hardiness zones. Hardiness zones are based on the coldest days of the year. Hardiness zones in the Midwest and Northeast range from Zone 3 in the north, where temperatures can dip more than 50 degrees below 0 Fahrenheit, and Zone 7, where the lowest temperatures may be between 5 and 10 degrees above 0. Let's walk through an example of how hardiness zones may change over the next several decades. In northern Illinois and northern Indiana, this area is currently a Zone 5B, meaning that they get down to about 15 to 10 degrees below 0 Fahrenheit. Within the next couple of decades, we expect that even under a low emission scenario, that area could shift to Zone 6. By mid-century, some parts of this area could be up to Zone 7. And under a high emission scenario, this area could be a Zone 8 by the end of the century. Heat zones are another way of determining habitat suitability for planting. These are based on the number of hot days each year above 86 degrees. Parts of northern Minnesota, Michigan, and New England have on average 1 to 7 days above this threshold, making them a Zone 2. In contrast, most of Missouri and southern Illinois and Indiana are considered Heat Zone 7, with 2 to 3 months above that threshold each year. Within the next few decades, heat zones are expected to shift north, especially in the southern part of the region. Under a high emission scenario, Missouri could shift to Zone 8 with 90 to 120 days above 86. And areas near Chicago could shift up to a Zone 7. By mid-century, Missouri could be a Zone 9 with 120 to 150 days above 86 degrees, and the Chicago region may be up to a Zone 8 under a high emission scenario. By the end of the century, shifts may be even more prominent in the northern part of the region, with all of the northern states potentially reaching Zone 7. Note that not much of a change is projected under the low emission scenarios, even by the end of the century. Besides shifts in suitable habitat and changes in heat and hardiness zone, what other impacts can we expect on our urban forests? Warming temperatures may also increase habitat suitability for insect pests. For example, the Hemlock woolly Adelgid's range is in part determined by winter low temperatures. Thus, it may expand northward, leading to more frequent outbreaks in northern states. Southern pine beetle is a major cause of disturbance to southern pine forests. This pest has expanded its range northward along the east coast recently, and models project that by the 2050s it could expand to much of the southern parts of the Midwest and New England. Bur Oak Blight has been an issue with bur oaks in the Midwest recently, and is believed to have benefited from wetter spring conditions that are becoming more common in the Midwest. Invasive plants may also benefit from milder winter temperatures. Kudzu, for example, is expected to expand its range northward as winters become more mild. A big change for our urban forests may be a longer growing season, with earlier spring and later fall, which could lead to increases in growth and productivity, but changes in winter and spring temperatures can lead to loss of cold hardening or more frost damage to trees that leaf out too early. Another impact along coastal areas might be an increase in salinity. Rising sea levels can contaminate the water supply, leading to widespread stress and mortality. So what do all of these impacts mean for individual trees? One way of evaluating these impacts on individual trees is by evaluating their adaptive capacity, or their ability to cope with change with minimal disruption. Trees with high adaptive capacity tend to have no major pests or disease issues. They're tolerant of flooding or drought. They're tolerant of things like wind and ice. They're salt tolerant, pollution tolerant, can live in a wide variety of soils and climates, disperse easily, regenerate easily, are shade tolerant, and require very little maintenance. Things with low adaptive capacity might be susceptible to one or more pests or disease that cause mortality or severe decline. They're intolerant of a lot of stressors like flooding, wind, drought, or ice. They can be sensitive to salt or pollution, have very specific habitat requirements, are poor dispersers, intolerant of shade, and require significant maintenance. An example of a species that's considered to have relatively high adaptive capacity is the Kentucky coffee tree. It has no major pest or disease issues, it's adaptable to a range of soils and climates, it's urban tolerant, and it has relatively low maintenance requirements and is widely available. A species that's considered to have low adaptive capacity is tulip tree or yellow poplar. This species is highly susceptible to ice damage and has relatively weak wood. It's intolerant of salt, intolerant of drought, and intolerant of flooding. Adaptive capacity can be combined with the information on the impacts of climate change to give you a sense of overall vulnerability of a species or ecosystem. Vulnerability can be defined as a function of a system's potential impacts, things like storms, heat, insect outbreaks, and adaptive capacity, or the ability of a system to cope with these impacts. Systems with positive impacts and high adaptive capacity are considered to have low vulnerability, and systems with negative impacts and low adaptive capacity are considered to have high vulnerability. We can combine the modeled changes in suitable habitat along with ratings of adaptive capacity to get an overall rating of vulnerability for a species. For example, if suitable habitat is projected to decline under a range of model scenarios and adaptive capacity is low, then vulnerability for that species would be high. If a species is supposed to gain suitable habitat and has high tolerance for a number of stressors, its vulnerability will be low. Now let's think about how that translates into the vulnerability of an entire urban forest or ecosystem. When assessing the vulnerability of an entire urban forest or ecosystem, it's important to keep other factors in mind. When assessing impacts, you'll want to consider how physical factors like elevation or soil type might affect your susceptibility to drought or flooding, for example. You'll also want to consider how biological factors, like a high proportion of vulnerable trees or the presence of particular pests or diseases, may make your impacts more pronounced. You want to also consider human influence, such as the amount of impervious surface, the influence of the urban heat island, or pest management in your particular site. When considering adaptive capacity of your urban forests, you'll want to consider biological factors such as the amount of biological or genetic diversity of your urban forests, the amount of funding available to support urban forestry efforts, organizational and technical factors such as the number of trained staff to do the work or how flexible your policies are. And finally, you'll want to consider social factors such as support from the community to assist with tree care and planting. I'd next like to walk through a few examples of how different urban forestry communities assess their vulnerability to climate change. The first example I'd like to share is from the village of Hazel Crest, located southwest of Chicago. Using a self-assessment, the municipal forester rated the overall vulnerability of Hazel Crest's urban forests as moderate to high. Impacts to this area included the fact that it had well-drained soils and made it more drought susceptible. It was very dominated by one species, silver maple, that was vulnerable to windstorms that they expect to increase. And many of their open lands were in low-lying areas and prone to flooding. They did have a number of adaptive capacity factors related to having a certified arborist on staff, but they also had low canopy diversity, lower financial resources, and not a ton of community support for tree care and planting. So their overall vulnerability was relatively high. The next example I'd like to share is the village of Riverside, located west of Chicago. Riverside is one of the first planned communities in the country, designed by Frederick Law Olmsted, who incorporated lots of natural elements, green spaces, and groupings of native species. This design has reduced the overall vulnerability of the community. though green spaces are threatened by things like deer herbivory and invasive species, much like many natural communities are. This area also has a large number of oak species that are susceptible to things like Bur Oak Blight and oak wilt. This area has a lot of positive adaptive capacity factors, however. The area has a diverse group of species, genotypes, and age classes. It has sufficient resources and has a trained forestry staff and a long-term plan. So their overall vulnerability was considered to be low to moderate. Here are a few things I'd like you to keep in mind as we move forward in this course from the things that we discussed today. Climate is already changing. We're already seeing changes in the area. Things are getting warmer, wetter in most of the area, and there's more heavy precipitation events. Climate changes are going to vary by location and season. We expect to see milder winters, wetter springs, and potentially low soil moisture in the summer. Habitat suitability for trees will shift. We generally expect habitat loss for northern species and gains for southern species, although this will vary from species to species. Trees vary in their capacity to adapt to climate change, and it's important to assess the adaptive capacity of individual trees. And when we assess our overall vulnerability, we want to combine our understanding of the impacts of climate change with the individual adaptive capacity of trees or of communities as a whole.